Yeah. So hello, everyone. Welcome to lovely 9 a.m. after a lovely conference weekend. So I'm glad you guys got yourself out of bed. This is totally fine. We're all good. We're going to talk about hacking through failure, and we're going to do a little bit of a spin on what you normally hear about some of these talks, which are, how we succeeded, how this went right, and, the cool stuff we've done. We're going to turn that on in its head and just say, we fucked up a lot doing this. This presentation, not the presentation, but the actual stuff, we messed up a lot, and we want to talk about those failures because I feel like that's not talked about enough. We're talking to other people. You need to realize that when you see someone doing a cool talk, you want to see them and their failures and what they tried and what they didn't try and what worked and what didn't. And so just about us, we're Detto employees who will often do CTFs together. We have the lovely Jonathan Beverly, who's specialty in reverse engineering. We have the lovely Ben Gardner, specialty in hardware. And then we have me, who was born in 1994. So I'm not a specialty in anything. So I'm just still a young guy. Give me time. I'll work on it. So it's just going to be a quick 45 minutes. We're going to talk about what we did in this challenge, the help we got, the stuff we did, the times we failed, and the times it didn't suck. Afterwards, questions. And if you want beers, it's a little early, but we will sit down with you for beers afterwards. That's totally fine. So RHME3 was a challenge procured by Riskier. It is a global competition of 500 teams. These are all the challenges that were part of it. There was about 19, if I'm not correct, 19 challenges that were done over a 4-month period. And we essentially said, hey, can we use some company resources to work on this? And they said, yes. And we said, really? And they said, yeah. And they're like, oh, yeah, that's amazing. Oh, thank you very much. I just handed some whiskey. So just to give you an idea, this was over a year of the timeline of what we were looking at. And so most of the challenges are within this 4-month period. So we just have them there because we're going to be just talking about them as we go through. But for the most part, the most important part of this timeline is, of course, this is unbearable smugness. This is what we've been experiencing since we finished the con. And it'll probably end when we're done our write-ups. I think so, right?
Is that a dig at me?
Yeah, he has to finish his write-ups, and nice. That's when we'll stop being unbearably smug about this whole thing. So, just themes, because we're going to give them right to you. This is an English class. You don't have to talk about the themes of what we're doing. Failure is part of the process. You need to use some outside resources. And do got innovation, which is innovating when you're in these dire straits and you need to just get it done. It doesn't have to be pretty. It doesn't have to be anything like that. And of course, we're unbearably smug, but the thing is, we came third. We didn't win. So, I mean,
that's part of why it's unbearable.
Yeah, it's unbearable because it's like, why you came third? So.
And the icon, right? So we're going to jump around quite a bit. And because we're going to jump around the timeline, we put like a little icon at the top, and you'll see that red bar jump around so you know like where in the competition we're talking about. It's going to be all over the place.
Yeah. So one of the most important things is, this is kind of have to thank people that were going for, but also to just let you guys know that, you guys drank with everybody here yesterday, maybe. Well, it's 9 a.m., so maybe you didn't. But we wanted to say that, you don't know everything. People are willing to help you about these types of things. So case in point, Ben.
Yeah.
We left you a reverse. Well, you asked to be left a reverse engineering challenge, right?
I just wanted to get like 50 points on reversing just myself.
Yeah. So there was a reverse engineering challenge, and he said, "Guys, leave it for me. I'll do it." And we said, "Sure."
And do you see the width of that black bar? Sorry, the red bar in the corner.
Yeah. So
that's 50.
The entirety.
That's Ben working on 50 points.
And the CTF, yeah. And so let other people do stuff, and we did, didn't we, Jonathan?
Yeah, you did.
Yeah. We gave it to Jonathan, and of course he did it in a day.
Day and a half.
So we said, all right, go ahead and do it. And he's like, I'm done already. So
I can't even refute that. That's
accurate. That's exactly what happened. We were able to get our coworkers' knowledge. We had no idea on how to do side channel. That was part of the challenges. So we were able to just be like, hey, lend me your ear for a couple seconds. I want to talk about, do you have a little moment to talk about the side channel analysis? And he's like, absolutely. So
Can someone tell us what that thing on the right is? Because it took us a long time to
yeah,
actually learn.
if you've never seen autocorrelation, it is the most magical looking thing you've ever seen. Yeah.
It's basically black magic.
It's basically black magic, and you're like, oh, there's the rounds of AES, but you're just like, okay, whatever. Yeah, it takes a little while. And of course, we had a bunch of help from Colin O'Flynn. We had Mr. Hughes, who gave us an extra spare board during the challenge. This was an embedded board that got shipped to us. It was like an Arduino MSP 430.
No, it was AVR X Mega 128A4U.
Wasn't even close. Yeah. So yeah, we got an extra board, and all these people we just kind of asked for help, and they gave us the help we're looking for. So you don't know everything. Sometimes imposter syndrome is correct. Sometimes, so just talk to some people. This is kind of a hacker space, and we're more than willing. Most of the people are more than willing to help you out a little bit. So going into the innovation stuff, Jonathan, you had an experience with this, right?
Yeah, I mean, like, Ben wasn't the only thing that beat his head against the wall sometimes. We had this challenge where we had a split CAN bus. We had two separate CAN controllers on this chip. They were talking to each other. One side was pretending to be an engine unit. The other side was pretending to be a dashboard. And the engine was, like, grinding and failing and throwing all sorts of errors. And the flux capacitor would only enable if you were able to maintain a speed of 88 miles an hour for about 5 or 6 seconds with no engine failures. And we were able to look at the messages going across. We spliced into the middle of the connection. And getting 88 miles an hour is easy. Just spoof the messages. Getting to no engine light was fine. You just had to black out all the problem messages and send I'm OK every once in a while. If you send both, everything glitches on you. Never worked. And I was tinkering, I was messing, I was doing things, and I would see it go up, I'd see it go down, I'd see it go up, and it was like up, down, flag, down, up, down.
Yeah.
Like, I never managed to get this thing hold up for more than 10 seconds, but 5 gets you a flag, so moving on.
Yeah.
Flag is a flag.
Yeah, because sometimes you need to do things the hard way. So you have to write your own stuff. You have to write your own stuff.
Tell us about the hard way, Jonathan.
So remember what Ben said about an AVR A4U X Mega? Have you heard of that chip before? Because it's got weak support in everything. The Mega itself is reasonably supported, but we had to write IDA processing modules to make this thing work. This right here is Colin's first attempt to make a IDA module. Yeah, it's like repfuscated.
Everything was a return, I think, at the end of it.
Yeah,
Everything was a return.
Everything was a return. And no.
Yeah, this is.
Yeah, so a big part of the beginning of the competition was actually tooling up on how we could reverse AVR X Mega. Because, the AT Mega was well supported. The X Mega changed a bunch of stuff. And when you try to open this in IDA Pro, what you really want to see is all the nice register names, so you can say, okay, who's talking to the serial port, who's messing with the time registers, where is the interrupts coming from, the important stuff. So I'm going to talk to you about some of the scripts we put together, okay? One of the first things is, we had a very specific X Mega chip, and IDA didn't have, like, the layout of all the places in memory and the size of the RAM and the ROM, but Atmel, now Microchip, actually publishes the entire programming interface for these chips in something that they call ATDF files, which are actually just XML files. So using someone else's, work that was put together for like creating other applications of the ATDF files, we started parsing them and created, our own idapro.cfg. So you could drop that into your directory, and then you'd have all the register names, and the RAM size would be correct, and everything would be correct, sort of, because that wasn't the only problem we ran into. So if you know anything about AT Mega, the whole register file is actually mapped at offset 0 in its RAM space, right? Which is kind of handy if you want to like save context, kind of neat. But on X Mega, they just decided, yeah, we don't need that shit anymore, and they just trashed it. So all of a sudden, your IDA Pro module thinks that all the offsets you gave it are all plus the register file. So we had to take all those nice, position information we had of all the named registers and move them all up by the register file that was now not present. And IDA also does like kind of a handy thing, they thought. The register names are actually read out of, the address names that you put on that register file in memory. So if we like moved everything up and then called a particular location at the low offsets, like USART 0, in our disassembly we would see a register USART 0, right? So what we did was actually take advantage of that, and a lot of X Mega uses what they call data vectors, a 16-bit value to point in the whole space, but you have to load it 8 bits at a time, okay? So you can actually like rename the locations in memory like ZL, ZH, as you're seeing in this screenshot here. And then when you're doing the disassembly and you see someone using Z+, you can actually go backwards and understand what filled in the low and the high parts of Z instead of, mentally having to remember that R18 and R19 are X.
R30 and 31.
See, he knows exactly. Okay. But then, of course, it's a 16-bit memory space, but the AVR can only really do 8-bit immediates. So it's kind of like ARM when you want to look at a 32-bit value, you have to load it in piecewise. And IDA, of course, if anyone's looked at IDA and ARM, does this really smart thing where it puts the two instructions together into a macro instruction, and you just see a load 32-bit immediate magic in the middle of your disassembly. So we tried to make a processor module. I mean, Colin did, but you saw how that went. Everything was a return. It wasn't really that great.
It wasn't that great.
No, it wasn't that great. But in the very first Riskier challenge, RHME won. Cisco had a write-up, and they just did kind of the naive thing. They just said, if there's ever sequential loads of 8-bit immediates into pair registers, just treat them as a data vector and create an XREF right there. And it's kind of like, the naive thing you would do. They didn't give us any code, but it was actually pretty straightforward to just write some crappy Python, because, that's basically what we do is write crappy Python.
Yeah.
Run it over the binary, and you got a bunch of false positives, but you did also get references. So the screenshot here is some more trolling from Riskier. They actually did things like this, and they put leet. See, it's referencing an offset in memory. The reason why you see 10, 1337 is IDA also doesn't handle segmented memory. What it does is makes a fake offset. So everything that's in RAM is also plus 100000, just for fun. Thanks. Of course, signatures are very important. No one likes to reverse things more than once. So we spent a bit of time trying to get signatures to work. The first thing we did was bang our head against Flare, right? And it turns out that no matter how hard you try, even if you patch the Flare signature generator, it will not work with AVR because AVR is what's called word-wise addressed, and it needs to be byte addressed for Flare to even work. And ILFAC is really nice. I don't know if anyone has a Hexrace support account. You go onto the forums and they're always very helpful, but unfortunately the answer was, yeah, don't do that. It's never going to work. Okay, thanks. So we tried Rizzo from Craig Hefner, and that did match some things, but just not enough. And we never really dug into why, because we found that BinDiff actually did the thing. So BinDiff, amazingly, on AVR code will do signature matching. The problem was that we could only build a reference binary with dwarf debugging information, and 695 had no idea how to do dwarf debugging with AVR, but 7 did. So we did the dumb dance where okay, here's a reference binary, load it up in 7, export all the names from the IDB, back into a 695 IDB, and then we could do diffs, and then we were good. And then the rest of the reversing challenge was basically you doing diffs against the reference binaries, which helped.
Helped. I mean, that's why I got something in a day and a half, right?
Oh, yeah, thanks for reminding me. Yeah, that's right. That was my job, I know. Right, so we did a few other things. We had some stack variables, which is really helpful. Everything used Y as a frame offset, so we could just scan functions and make stack variables. It's nice. And of course, something that you have to do with every flat binary is emulate the loader loop, right? You have to make sure that your .data section that the linker put in always gets copied into RAM, and you want to actually copy that data yourself because you want to have the XREFs line up. That's not unique to AVR. You just do that with flat binaries. And of course, we made a script to kind of help us with that. And so if you ever find yourself having to reverse some Xmega code, there are now some, crappy Python scripts that should be able to help you. Yeah, there you go.
And remember how this started with use other people for help? Ask us. We'll totally help you make this work.
How to sidechannel?
How to sidechannel. So sidechannel analysis requires a bit of setup. There's a few parts involved. There was a month of us trying to figure out how to do this right and make it work and get good signals out. This is the setup we ended up with. The battery pack is really important. It turns out that if you try and use a board that's being powered over USB, because the desktop is doing so much stuff, its power plane is very noisy, so you're going to pollute all your signals. So we ran power off a battery pack. They have a very clean power input. You also need some way to drive your board with very low latency and very high efficiency. So we have there an $80 80 megahertz toggler. This is a JTagulator that was reprogrammed to do nothing but when it gets us nothing but send a single byte every time it gets a power line going high, so the picoscope could trigger off the board efficiently. But make do with what you have. You also need tools. You cannot just do sidechannel by yourself with crappy Python scripts. This is the Riskier Inspector. The Riskier Inspector is a very expensive, very nice tool that some of our coworkers have because they do sidechannel analysis professionally. Great, we got to borrow it. Fantastic. It does everything. This tool was built by them to use in-house to side channel analysis professionally on huge consulting gigs. It's great. You just have to write everything yourself using barely documented APIs in Java. One of our coworkers trained on how to do this. He was way too busy and couldn't help us. Moving on. So we went to the Chip Whisperer. The Chip Whisperer is a fantastic project. It does all sorts of cool things. It was also undergoing a major revision from 3.50 to 4.0.0 at the time. The wiki was full of dead links. Half the projects didn't work. Modules, we backported a module from 4 to 3 to try and get better performance, and that pooped all over everything. And then we got a hardware fault, and our FPGA locked up and just channeled the entire power input through the FET until the FET melted down. And so we ended up with broken hardware and broken software. So let's just, Chip Whisperer is a great project. And if you need to do side channel analysis and your budget is less than $1,000, it's basically the only way to get it done. And then we got to JLSCA. JLSCA is a side project done by a couple of riskier guys, the same people making the inspector almost. And it's fantastic. It's like, they even had a bunch of RHME2 challenges that were done in a tutorial repo that we could pull down and look at. And the actual attack I needed to implement was based on this paper by Ilya Kishkatov. And Ilya Kishkatov is one of the authors of JLSCA. And a previous challenge, it literally is a module that does exactly what we need, except it's targeting the wrong hardware, so we have to fix that later. There's just a few really strange things with JLSCA because it's written in Julia. And if you look at the screen, you will see there that there is an XOR operator written in the math style. That's a Unicode character as an operator right in the middle of my source. If you know anything about S-boxes, you know that S-boxes are like you take a byte, you put it into the S-box, you get a different byte out. Why am I adding 1 to the thing I'm passing into my S-box? Because arrays start at 1. It's every single day, all my coworkers will attest to me screaming arrays start at 1 because it screwed everything up all the time.
Yeah. So that was a lot of tough stuff, right? That was a lot of us having to put some brain power. But the thing is sometimes when you're in this you-got innovation and you're really pressed against the wall, what you really need to do sometimes is just brute force things.
Yeah, I love how you frame that this is like no brain power. This is like the dumb thing. Thanks for that. So what you saw in the past was that parallel setup of brute forcing. We're actually in tandem brute forcing one of these challenges called car key fob, okay? The reason we had to brute force is I have a signal diagram here to try to explain to you what car key fob was. It was 3 major sections where you could shift data in and out over what turned out to be sort of bidirectional SPI channel, but it was described in the channel notes as a scan chain. So of course we tried JTAG first, but that's actually a later slide. So you got a chance to send in some stuff, and it turns out that there was flags to set. You could set a bit that would give you back a challenge, or you could set a bit and the board would self-destruct. It would count down, and then it would say fake explosion, boom, go away. It was kind of funny. And then you got this other frame, the next one, where you'd get that yellow bit, you get the challenge out, and this was a 16-byte random number, and that's all we knew. It was just clearly random and 16 bytes. That's it. That's all you get. And then you knew that you could do another latch, and you would only get a chance to send 384 bits, and after that, the system would just reset. And this is all we knew at this point. We knew it was a challenge response. We knew that we'd had a random 16-byte value. We didn't know the algorithm. We didn't know how to put together the response. So when we say we're brute forcing, the scripts were brute forcing all possible algorithms and all possible positions.
And all possible endiannesses.
And all possible endiannesses, yeah. The way that we had the script set up ended up being this weird functional programming with lambdas so that we could pass in strategies, and the code was just terrible. You don't even want to look at this code again. So that particular run, that was when we had finally learned what the password list was. Because eventually they realized no one's solving this challenge, so they kept putting out hints, okay? And the day after they said, okay guys, the password list is this, and you have to pick 2 of the words from it to make 16 bytes. Go. And they're oh my God, we know how to solve this, right? I mean, it's done. This is a tractable list. Go. So we put 2 laptops next to each other, and we just said, do the thing on half of this, do a little bit of overlap on this other one, and we're definitely going to get it tomorrow, right? We didn't. We did not get it tomorrow. This went on for ages.
Yeah.
For ages. Go ahead.
A month and a half of brute forcing?
Yeah. So Ben does client-side visits.
Yeah.
And so he battery powered the board, and he would take it with him in the car, and he would brute force while he was going to customer sites and just leave it running while in the car. And he would also, do we want to go to the next?
Yeah, we could talk about it.
Well, we can talk about this, yeah. He took it on a plane.
I did. I know, it seems like a terrible idea, but I would have had to restart like an 8-hour run. So, I mean, like, what was I going to do?
What was he going to do except board a plane with a embedded system with a bunch of wires coming out of it?
Yep. I know.
Yeah.
I know. It sounds really dumb, but it didn't at the time.
Yeah.
It sounded like a great idea at the time.
So they're actually pretty nice. Just if you
watch, the attendant will offer to hold my laptop. She's like, "Can I hold that for you?"
Can I hold? Can I
like
hold your
numbers
weird
are
electronics?
scrolling and lights are blinking. Yeah, they're extremely nice about it. I'm like, "No, I got it. It's fine. It's no problem. But thank you so much." She's like, "That looks very important." Thank you. The guy behind me in line was not cool with it. He was not cool with this at all.
Yeah, so this was almost not in the
You're
slide.
right. We almost took this slide out.
We almost took this slide out.
3 days ago, someone who's involved in aviation security, like someone that I would trust is actually telling the truth here, sent me a message saying, "Hey, a friend from Delta just called me. Did you try to board a plane with a whole bunch of wires hanging out?" And I was like, "Oh, shit."
Yeah.
And you can see at the bottom, she asked me exactly that. "Did you board, ? Bunch of wires, laptop open?" And what was I going to say? Like, actually, yeah, I did that. I'm stupid, right? So we were going to drop this slide, and then the next morning, I got pranked. I got super pranked hard. The guy who took that video of me boarding knew the person involved in aviation security and told her about it, and then they did that chat. So the whole thing was a prank. I got pranked super hard.
They were going to send you an email telling you they were joking, but they sent it to the wrong email address.
That's right.
So this is in the slides now, and he was the most stressed out I've ever seen in my life.
Yeah, he was like calling his lawyer and sweating bullets.
His lawyer, so it was
his business involves flying to customer sites all the time, right?
Yeah, no fly list would be a big deal.
Yeah.
But the good news is you can board a plane with like a box that, is blinking lights and wires.
Yeah.
Go for it.
Just wear a suit. Wear a suit. That
works.
Yeah.
Yeah, it works. So tell us about sometimes how it's only the hard way.
Yeah.
Well, yeah, I mean, like, this is a car crash. It was actually a pretty quick challenge compared to a bunch of the other ones. And it was pretty quick because rather than trying cute stuff, I realized pretty early that it was just grind your way through it, do it the hard way. Because sometimes when you're given a couple kilobytes of binary that are doing some sort of obscure off-label crypto algorithm that's broken that you need to patch, the only way to make it work is you read the whole thing, you decompile the whole thing by hand because no one supports decompiling AVR, you make that decompiled code build all by yourself, and then you run that thing in a debugger side by side with the binary and an emulator so you can make it bug for bug compatible. And then instead of having to reverse an AVR shitty binary, you get to reverse C. And the C is doing you get both encryption and decryption in this code, and they don't match. What you encrypt and what you decrypt just is noise. So you just have to find out where the bug is in the decryption code, and suddenly you get a flag. Easy in C. In AVR, reversing crypto by hand in binary, you've got to be fucking kidding me.
I mean, and sometimes you got to break all the rules. We talked about his lovely airport companion that he had with him. We actually had to. This you cannot buy. This is a cable you can't buy. We had we were looking for Stack Overflow about how it's illegal, but you couldn't find a screenshot of it. But this is a split USB cable, so half the power comes from one side, where it comes with a battery pack, and the actual data goes to a computer. So we actually did that. You did that splitting, correct?
Yeah, I'm a sucker for rework. All the rework is me.
All the rework is him. Yeah.
Yeah. So the previous slide about battery packs, the data still has to come from the desktop, right? Yeah. So the data lines are going to the desktop, and the power lines are going to the battery pack. And make sure you plug them in the right order, or the battery pack will be like, "There's nobody on the other side. I'm turning off." And it'll wait 2 or 3 minutes first. So you're in the middle of a run, and just battery pack is just like, "Nope," and walks away.
I mean, you did a lot of rework for the challenge, but.
Totally. But it wasn't pretty.
It wasn't pretty. I mean, sometimes we took this. We had a fault injection. We had to make our own fault injection rig, and this is from like a random graphics card. We went to electronic stores and they didn't have a fast enough transistor. We went to we raided garbage. We went to the company.
Yeah, the other one we built was from a dumpster.
Yeah, we got that from a dumpster, And so we made a fault injection rig using that. But essentially, like when you're dealing with this kind of innovation stuff, you really just it doesn't have to be pretty. Just let it be a. That looks lovely because it's got the rainbow cables, but everybody's.
It looks pretty to me, but
yeah. It does like stuff like that. It doesn't have to be pretty. Just like make it a mess of wires, make it work, and curse yourself when you realize like that wire came unplugged because of course it's you have it connected like that.
By the way, don't mock the dumpster. If your company has an e-waste dumpster, it is full of components if you ever need them.
Yeah. So when you're trying to do this type of stuff, just brute force it when necessary. If you have to do hard work, if you have to just grind your teeth, do that. And if it's ugly but it works,
Then
is it
it
really
works.
ugly? Is the question.
flags.
Yeah,
Flags.
flags. Yeah, if it gives you the flag, is it really that bad of a solution? No, it's the right solution.
Move fast and break things, other people's things.
Yeah, other people's things.
Other
And
people's
we broke a lot of stuff. And we failed in numerous ways, I think.
Yeah, let's talk about our failures.
Let's talk
That's
about
the biggest
yeah,
section.
we're pumping ourselves up, but we fucked up a lot. Like as you said in the first second slide, like this was our qualifier challenge that we would have been qualified.
Yeah,
And,
so if you remember, like the green timeline, qualifiers actually started in August before January. Like the qualifiers for this were in the middle of the summer. I'm on vacation with my family, like at Disney World. You guys were in the middle of like an assessment, so you couldn't help. And I'm like by myself, but it's fine. They make this thing called side channel marvels, and you can run binaries in an execution tracer. What you're looking at on the green and red is like an execution trace. And you can see it reading the instructions. And if you look at that sawtooth on the right, that's actually AES, right? It's every round of AES going over the same kind of SBox each time and changing the data as it goes. And when you have these execution traces, it turns out you can use something really similar to power analysis. It's just differential computation analysis. I didn't write it, but I did git clone a repo and run it. And so it gets the key, right? Like there's the key, that's the flag, boom, I'm done. Paste, didn't work. Okay, maybe lowercase, no, uppercase. Spaces in between the bytes. Did I try lowercase?
You tried everything.
I tried lowercase.
Except
it was
converted to
actually
ASCII.
Like I'm just an idiot who is ASCII.
Yeah, so for qualifiers, he had the right flag, he just
Exactly.
didn't convert it to ASCII.
Yeah. So we didn't qualify in that qualifier.
didn't-
There's
yeah.
a second chance qualifier, and that's how we got in because I fucked this up.
Jonathan, how did you mess up?
This one is, there was a lot of mess up. This one was, I spent like an entire weekend reversing the shitty AVR code to do some sort of fucked up. No, it wasn't that. It was CAN binaries, and the CAN, if you got it right, you could convince the board to dump its own firmware over CAN bus, and if it did that, you could start reversing the firmware and finding the flags, except when I was in the middle, actually just before I started reversing, literally like a day before I start reversing, they push an update. I'm looking over here, I'm reversing the old binary, I go through the old binary, I get past the fact that the old binary is broken, I get the flag out of the old binary, I submit it, nothing happens. Because of course, when they changed the challenge, they also changed all the flags.
Yeah. So he was reversing a broken binary, essentially. He still got it, but it wasn't the right answer anymore.
Nope.
Yeah. Yeah. So this one, this was
Yeah.
almost a...
Yeah.
I
Yeah.
almost didn't get this one.
I come from a math background, so I really believe that 99% right is still wrong, so. If you're 99% of the way to the flag, it's not a flag. In this one, this challenge is frigging insane. It's a cheap challenge, it's a small challenge. 2 weeks of solid reversing. It took 30 minutes to send the correct payload to the board using this ASCII pulse dialing system. You want to send 32 bytes over, you want your first byte to be hex OX, hex OF, you got to hit the button 15 times, wait a second, it logs one character. You want to send hex 128 times, wait a second, it goes through. Sending this password in, it's not 32 characters. It's 32 characters wide by 10 lines long. It's this huge block of ASCII text you have to throw in, 30 minutes to clock it in over the serial line. The thing spends 6 hours processing to make sure it's the right value, and by processing I mean a 500 million iteration busy wait. And then it'll drop the flag for you.
Well, it will.
It was supposed to.
It was supposed to.
Yeah, so these guys are walking away with the board because they're going to do other things with it all weekend. And I'm like, it'll be in password.log, just like cat it. And they're like, nothing.
Cat
nothing,
password.log.
Nothing.
Nope. Cat password.log.
Do it again.
Nope.
Yeah.
Yeah, because output buffers are a thing. And so
Yeah.
it was sitting in the output buffer.
It wasn't in the file, it was in the output buffer. So we finally catted that, and then
Yeah, this guy over here actually thought of it like seconds before when I said, sorry, I fucked up, it must be nowhere. This guy's like, wait a sec, I'll cat the buffer. Boom.
yeah. So this is our glitching rig. So we got
Sorry, bad memories. Go ahead.
Bad memories. Yeah. This was we had to do some data glitching with our glitch rig. So there's a bunch of pulling the power down. This thing is very sensitive. This is like if our whole challenge was a band, this would be your bass player. Like he just moody, and like if you put the power too low for like just a tad bit too long, that thing would like reboot. So we had to do data glitching based on that, and we actually did do it, but unfortunately,
You keep saying we had to do data glitching. We had to do clock glitching.
We had to do clock glitching.
We did data glitching.
We did data glitching. Yeah, you're right.
Yeah,
Sorry.
exactly. That's the problem.
Like we could manipulate, when it went to RAM and said, hey, I need a value, we could supply the right values and that would work. The problem is in order to make the challenge succeed, we had to branch jam. And we couldn't jam the branch off the data read because the branch was all in registers. So what we needed to do was we needed to skip the branch instruction. You can't do that with data glitching.
So what you see here is we did get a data glitch set, and it went down the right path halfway through the binary, and it says your flag is FFFFFFFFFFFF.
Yeah, they have a mask on it that won't print out
That's
the
not a
flag.
flag.
Yeah.
There's a two-part thing. Like that's literally trying to print the flag out. But before it prints the flag out, it ORs it with this byte that it's got stored in memory that we were supposed to zero before we got there.
Yeah. So we were very sad when that happened.
Yep, that sucked.
Yeah. Speaking of being sad about a bunch of stuff, this we're gonna have some audio for this in a little bit, but this was it came out as an audio stream. Like one of the challenges, all you had to do was look at the audio stream. We thought it was JTAG. We thought it was a bunch of video output. It just turns out to be sound.
Yes. Tear the jack off a pair of headphones, plug it into the board, you hear audio.
Yeah. So that took us a while, and. The thing about this one is there was two parts. There was one part where it was just connected, but then there was this other part where you had to brute force this thing. And it would say that every time.
Yeah, I think I listened to this like 200 times
This is a
in my
table.
basement. This is the table. This is half the table I created while doing this connect back, where you do these like flyback connections. And you do a connection, reboot the board, and listen to this.
Again.
And then do it again.
And again.
And again. Yeah. Man.
And then it would do that again. And so that represents, this is a brute force. He created this table and he said, guys, I've tried all of these combinations and I can't get it.
I tried
didn't get
PA
it.
5, 6, 4, 3, 2, 1. I mean, I tried all the PAs, right?
Yeah. All PAs.
Every PA that was on the silk screen.
Yeah. All of them.
I didn't read the damn schematic.
But you know, what
I just
about that
needed
other
to
one?
read
What about
the
that other one that was
schematic.
there? What about that giant table? But there was, yeah. So
Yeah.
we had PA 0 that we totally missed. So we did that entire table. We brute forced the entire thing, and we were missing an input.
Yeah, more failure. That's on me.
Yeah.
Yeah. What's the tally at? That's a lot of failure.
Innumerable.
Never mind. Don't answer the question. Don't answer that.
Yeah.
Right, so sometimes you fail because you have a hammer and everything looks like a nail. I had a JTagulator. I love my JTagulator. And the challenge description for car key fob said scan chain. So I'm immediately like, oh, that's obviously JTAG, right? Wrong. It was not JTAG. And they made it rate limited, right? You could only bit bang car key fob at like, I think it was like 4 kilohertz. That was like the maximum speed that you could go, right? Which meant that this kind of thing for JTagulating all the 4 pins took like, 2 days. And the answer was nope. And this is one capture here is you can see it triggering the self-destruct, right? Because you try to do JTagulation, it would hit that one bit, just through random action that causes the self-destruct, and then the board would lock. So part of this process was like, oh, it's self-destructed. I have to like restart the JTagulation at a different phase. And yeah, that didn't work either. So yeah, this is the failure category. None of this stuff worked, just so you know.
Yeah. Is this JTAG? Yeah.
This was us. This was us, yeah.
Yeah. But the thing, like, we're talking about all our failures that are our fault. We brute force this, we brute force that, we missed a silk screen lining, or we didn't, or we didn't convert it to ASCII.
Wow.
Or but there is some stuff that aren't our fault, and one of the ones is car key fob.
That was not my fault.
That was not our fault. That would.
Was it your fault?
It was not my fault.
It wasn't
This
our
one
fault.
was not
This was
my fault.
not our fault. This is.
Not my fault.
Yeah. Okay. When doing side channel to transition to some side channel analysis stuff, don't elastic align is just a tidbit I just wanted to share with you guys because that takes forever and you can just static align. You really don't need it that aligned. We wasted a ton of time doing that stuff where it's like, hey, let me run this elastic align. All right, see you in 3 days with this like crazy overpowered CPU, and we're just like,
Yeah, we got to borrow their quad-core Xeon for grinding on things because they didn't need it all the time, and I ran a 100-hour job to align this thing.
Yeah.
Didn't get us anything.
Didn't get us anything. So sometimes when the solution with side channel is sometimes brute force is the normal way to do it, you gotta have to do it a different way. We tried clock injection too, as I mentioned in the thing.
Yeah, the problem was the voltage limits. Like they have a brownout detection in the AT megas, and Riskier had set the brownout detection very, very stringently. It's part of the reason why we couldn't instruction glitch. Like any significant change to the power rail would trip the brownout detection, and the system would lock up until you hard reset it, right? But we did try this because when you're trying to do a fault injection, you really want to do it synchronously to the CPU clock. But they configured the X-Mega to have an internal RC oscillator and not accept any inputs at all. There is something you can try through sympathetic resonance to actually inject a modulated signal on top of the power rail, and then just kind of like if people like walk in march step, like soldiers break march step when they go over bridges because of sympathetic resonance, right? If you kind of go all at the same time, push things, everything pulls into phase. Okay, so it's the same idea, but long story short, it did not work. Every time we fighting got a lock, it would also trip brownout detection. So clock injection didn't work.
Yeah, it's actually funny.
But we tried it though.
Yeah, it's funny you mentioned soldering there because
thanks, yeah.
we actually tried to do clock recovery. This is my fault.
Yeah,
this isn't his fault. This is a break from the norm here. We tried to do a clock recovery board. I was responsible for ordering all the parts. I did not know the difference between an 0603 and an 0402 or a 201.
Yeah, thanks, Colin.
Yeah, so you actually soldered that in the end. It was two giant glob bridges.
I did. I was like cursing your name the entire time. But
Yeah,
I did
yeah,
actually
yeah.
solder those components, yeah.
You soldered it, and then it didn't work. It didn't work at the end. Because I
thanks,
designed
Colin.
Didn't I design it?
Yeah, it was your
I
design.
did design it, didn't I? Yeah, so that's another failure we had. So you will fail, varying ways. But the thing about failing in this way and in this hacker space is that you're when you fail in weird ways, it means you're doing really cool stuff. Is essentially what it comes down to. And
That's a nice way to put it.
and when you fail in weird ways and you actually don't fail for once, you just get to enjoy the Eurekas. You get to enjoy those good. So we're gonna
Let's talk about some things we didn't fuck up.
let's talk about that.
Yeah.
That for a little bit.
Car key fob was not my fault.
Was not his fault.
Yeah.
They shipped a wrong version of the binary that did not solve. So we did an entirely brute force of it, and
Yeah, we brute forced the entire space, and eventually we ended up convincing them that we should have got the flag because we exhausted the entire search space of all the algorithms and positions in this register, and we sent them the write-up and the code, and it forced them to go back and verify that they hadn't QA'd the binary that they shipped us.
yeah.
Right? So the challenge was bugged. There was no way we could have possibly solved this. And like you see the bar, right? That bar means that was 4 months of us just like banging our heads against this challenge.
That didn't have a solution.
They didn't have a solution.
Yeah.
But we got the gold star de facto, and I was like, good, I'm never doing this again. Shut. Done. I still don't know what the actual solution is.
Yeah, we don't know.
We got a
Yeah.
de facto gold star, and that was good enough for me. I was done.
Not de facto, retroactive.
Retroactive gold
Retroactively, yeah.
star. Yeah.
There's some whining online when someone realized that we got the gold star before they submitted the patch that allowed you to get it.
Yeah, they were like, why does this team have it? It's like, well, because we submitted like a page
Yeah.
page write-up.
Demonstrated 4 months of brute forcing, and that was good enough for Riskier. So.
But yeah, some other weird ones. Yeah.
Sure. So the imposters. The imposters was bizarre. I mean, so it's called the imposters. They're talking about fake things, and you look at it in our autocorrelation. You see 16 rounds of AES clear as day. AES 128, 10 rounds. So what are the other 6?
No problem.
What are the other 6 rounds? Obviously, they're fake. So I spent a lot of time reading about fake rounds, figuring out how to look at things. As it turns out, 15 of the 16 rounds are fake. There is one real AES thing in there, and it's hardware AES doing the whole AES in the exact same times it takes a regular software AES to do a single round. So right there, that would normally be a single round, but that's actually the whole in crypto happening right there. Super fast, super efficient.
It wasn't hard.
So with Ben's help, we made this lovely differential probe, and
It's cute, wasn't it?
it's gorgeous, and it does the job great, and we got huge signals, and we ran all the attacks on it, and read Ilya Kishkatov's paper, and implemented everything, and no flag. And so eventually, I decided to do things the hard way. I got that board there, which you might notice if you've been paying a lot of attention, isn't the same board, but it is the same chip. And when we had that, we wrote the code that we thought would do what they thought would do. So we wrote our own hardware AES crypto code with the same sort of inputs and the same sort of outputs, put it into the same side channel analysis rig, and then we know what the key is, we know what the input is, we know what the output is, we have to be able to find this correlation. And over hours of analysis, I eventually sent this text on the Slack channel, and these two people were busting a gut laughing over what the hell I was talking about. But that picture right in the bottom center is a picture of an AES state vector, and I've drawn lines between where the correlations are. The correlations happen between pairs of values, and they happen in shift rows order. Because of the wonderful loveliness of Julia, it's like a math language. It loves vectors and matrices. This is a one-line patch. Like, it took me 5 seconds to code it up. I was just like, take this vector, reform it into a 4x4 vector, do an AES shift rows operation on it, reform it into a linear vector, do the thing you need to do with it. One line, just done, and suddenly we have a flag falling out.
Yep.
And I still tell this story because it's the funniest challenge ever. You get a board with encrypted firmware. You send 16 bytes in. It gives you 16 bytes of ciphertext out. That is everything you have. Get the flag, and I fucking did it.
That's awesome. Super awesome.
Yeah, I mean, we got to go to our own horns and bring up that unbearable smugness. I mean, we got a lot of flag. And
this is why we're unbearably.
This is why unbearably smug is. These are all when you're enjoying the Eurekas, just patching together. We were doing Slack and stuff, and this was just we just put it together and just looking at it gives us the warm and fuzzies a little bit.
Yeah, I like to look at this picture too much. It's not healthy.
Yeah, it's screens like our background and our screensaver and our maybe it's on our phone, maybe it's it's an alarm when we wake up. It's on our phone. Yeah. But yeah, no, I mean, section summary, we're unbearably smug.
We didn't win. We placed third.
We placed third, so I don't know why.
We're talking it up a lot.
Yeah, we're talking it up a lot, but
third of 500 is not bad.
Yeah.
First in Canada.
Yep. So, I mean, we're winding down. Do we have any questions before we end this?
Yeah, as we prepare to close, anyone have any questions? I know we talked pretty fast.
Yeah.
Cool. All good?
All right. We almost have our full write-up. So he has to finish Kharkiv fob. That wasn't his fault.
I'm never doing that write-up. It's never going to happen.
So it's done. You can find our write-ups there. They're really fun. There's a lot of swearing and a lot of making fun of arrays starting at 1. Yeah. Thanks, guys.